Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Welcome to MIT's Faculty Forum Online. I'm Fatima Hussein, a graduate student in the MIT Department of Earth, Atmospheric and Planetary Sciences, and I'm your moderator today for this exciting event. I'd like to extend a special thanks to our sponsors today, the MIT Federal Credit Union and MIT Professional Education, for making today's exciting event possible. Before we begin, I'd like to extend to you all a reminder that after we hear from today's experts, we'll dive into an exciting Q&A. Please use the Q&A feature on your Zoom toolbar to ask all your burning questions about Mars, and we'll get to as many as we can as time allows. Now I have the distinct pleasure of introducing you all to Tanya Bosak and Benjamin Weiss, both professors in MIT EAPS and both investigators for the Mars 2020 Perseverance mission and members of its 10-person return sample science team. Like them, you may be excited by the prospect of this mission landing on Mars next week. I know I certainly am. With our experts, we'll discuss the landing, exploration of the Jezero crater for signs of ancient life, the capabilities of the Perseverance rover, and the prospect of returning rock and soil samples to Earth. For more information, we'll post a link to their full bios in the chat now. But for now, I'd like to welcome Professor Bosak and Weiss. Welcome.
Hi.
Thank you, Fatima.
All right, should we take it away? Okay, so we're going to begin by sharing with you some thoughts we have about Mars 2020, and then we'll go to this question and answer section. So I will share my screen. Okay.
And presentation.
All right. So welcome all. I'm Ben Weiss, and here's Tanya next to me. Today we're going to tell you about our work associated with NASA's next lander on Mars, the Mars 2020 mission, otherwise known as Perseverance. It's going to make a big leap forward in Mars exploration because it'll initiate the campaign to return samples from Mars to Earth for the first time. An eventual analysis of these samples in Earth laboratories, which will probably go on for decades, will address two big questions in Mars science. Was ancient Mars habitable, and was there past life on Mars? And we're going to talk to you about each of those questions and our work associated with it. So Mars today is cold and dry. The average surface temperature is like -60 Celsius, and the surface pressure is 10,000 times less than that of the Earth. So not only is the temperature is too low for water to go into a liquid form, it turns out even if it, when it gets up to 0 C, it goes straight to a gas. So, I should have said 7 millibars of pressure and 10,000 times less water. So anyway, Mars has long been an object of fascination for planetary scientists in the search for extraterrestrial life because of images like this. So this one was taken by the Viking orbiter in 1976. And what you can see here are two kind of populations of craters. So you have really sharp craters, which are very well defined, like this one here, which are relatively young, and this one right here. And then you see some other ones that are like much older and really kind of weathered and flat floored and are dissected by these ancient river networks here, which we call valley networks. And so what you can see is that there was some dramatic change in the climate of Mars over the last several billion years. Apparently, prior to about 3.8 billion years ago, Mars was warmer and wetter, and water even flowed on its surface. So what happened and whether Mars was habitable at that early time is something that's been of intense interest ever since images like this came back. Okay, here's an example of another one of those craters. This one is called Jezero crater. And what you can see here is you can barely see the crater because it's filled with sedimentary materials. And they were produced by ancient liquid water that flowed through this valley network here on the left, flowed into the crater. It actually filled the crater all the way up, we think, with water. And eventually the water leaked out the other side, as you can see here. And the Jezero crater is this ancient lake bed that's the landing site for the Mars 2020 rover. Okay, so let's zoom into the left side of this, where the rover is going to land. And what you can see here is what looks like an ancient river network, what you might see at the end of the Mississippi River in North America. And you see here, this is a kind of a false color map where the colors are denote minerals that have been inferred to exist on the surface. So greens and blues are carbonate minerals. So these are things that make up limestone or reefs on the earth. We have orange things like olivine and purple things like pyroxene. So these are things that may make up basalts, or they may be sedimentary rocks made out of lavas that were eroded away and then redeposited. And this is where the landing site is going to, hope it will be in less than a week. So you can see water flowed in here from the left and then deposited this beautiful fan at the right, which we're going to explore. It's called Jezero Crater. Turns out Jezero means lake, and it's actually a place in Bosnia, in Jezero. It's a little village, and here's my Croatian cousin for scale. And I should mention, Tanya and I are married, in case you're wondering why we're sitting next to each other, and Tanya is from Croatia. Anyway, here is the Mars 2020 rover, and it's bristling with all kinds of fascinating instruments. It's got this camera on the mast here, which is it takes stereo images and high definition video. It's got a laser that it shoots that makes plasma out of the rocks that'll be sensed using a spectrometer to infer the composition of the rocks. And it's most importantly, it's got this arm that keeps coming out that you'll see. And on the end of that arm, along with imagers, is a drill. So the goal of this mission is to drill samples on Mars with the idea that hopefully in the next decade or so, they will be brought back to Earth for the first time. Also for fun, the mission has a technology demonstration, the Ingenuity Mars helicopter. And if all goes well, this will be the first controlled powered flight on another planet. We're expecting to land next week, February 18th at 3:55 p.m. And we hope you can all join us online for the live footage, which is going to be spectacular. The rover is equipped with all kinds of cameras, and that you'll be able to ride in and watch the landing happen almost in real time, like we've never seen before. So, as I mentioned, the defining goal of this mission is to ultimately select and drill samples for the first time, and that's the role that Tanya and I are playing, is in the selection and documentation, and if we hope eventually analysis if these samples come back on Earth. So we have two sort of big questions that we hope to answer with these. One, why did climate change on Mars? And was there actually early life on Mars? So I'm going to talk about the first question, then I'll pass it over to Tanya to talk about the second question. All right, so why did climate change? So as I mentioned, billions of years ago, Mars was apparently warm and wetter, with water possibly flowing across the surface. And today it's cold and dry with liquid water not even stable on the surface. So what happened to Mars? It may be intimately connected with the history of the Martian magnetic field. So today, Mars does not have a magnetic field like the Earth, generated by churning of its liquid metallic core. But we see from previous spacecraft measurements at orbiters that there's strong magnetic fields coming out of the rocky crust of Mars, as plotted on the right here. You're looking at the radial component, the out of the surface component of the magnetic field at 400 kilometers altitude on the right. And you see there's very strong magnetic fields in the southern hemisphere. In fact, so strong that if you were to walk around on the surface in that area, you'd see that the field strength is basically the same strength as Earth's today. But the fields are very complicated. So apparently ancient Mars had a magnetic field that has since gone away. Also, it turns out that Mars, this crust, must be loaded with magnetic minerals in order to be so magnetic. I'm going to come back to that question, what is making the Mars so magnetic in a few minutes. It's related to the question of habitability. All right, so we also have a rock record of Mars. These are meteorites that were blasted off the surface of Mars and naturally transferred to Earth. As a graduate student, I worked on one of these, ALH 8400, found in Antarctica, and we found that it too contains a record of ancient magnetic fields. So billions of years ago, Mars had a magnetic field and it was apparently strong. So this is really important because on a planet like the Earth today, which has a strong magnetic field, the atmosphere is protected from stripping by this high energy plasma coming from the sun, known as solar wind, and moving at hypervelocity. But if planets without magnetic fields like Mars today, the atmosphere is directly interacting with the solar wind, which is stripping away the outer layers of the atmosphere. And if that goes on for a long time, it can substantially deplete the atmosphere of a planet. So one of the leading ideas why Mars may have lost its atmosphere is that it may be related to the loss of protection from the end of the early magnetic field. And the reason that's so compelling is that we apparently, from studies of magnetization in that Martian meteorite and from the crust, we see that there was an ancient magnetic field generated in the core of Mars, what we call a dynamo, at least 4 billion years ago, possibly extending all the way back to near the formation of Mars at 4.5 billion years ago, and maybe is extending as recently as about 3.6 or 3.7 billion years ago. So basically, this is very deep in Martian history. It's about as old as the time we have rocks on Earth. This just so happens to coincide at the end of the possible end of this magnetic field, which is poorly dated, as you can see, with the timing of ancient aqueous activity on the surface of Mars, the so-called valley networks that I showed you earlier. It seems that maybe the end of the magnetic field may have coincided with the end of this early period of aqueous activity. So we could test this idea by determining how strong the ancient field of Mars was and when it died. And for example, if it died before the period of climate change, that would be consistent with the hypothesis that the reason Mars lost its atmosphere and its surface became largely inhospitable is because of the death of the magnetic field. So how could we, or how will we test this with Mars 2020, the Perseverance rover? So here is that same landing site again, of the delta in the middle. Now I've overlaid on it colors to denote the ages of different surfaces. And we infer these based on the number of craters on the surface. The higher the density of craters, the older the surfaces. So I'm using this term GA for billions of years ago. So what you see is the floor of the crater, the purple region on the right, is about 2.2 to 3.5 billion years. It's actually fairly uncertain. And then there is the delta itself, the fan, which is older, about 3.7 to 3.9 billion. And what's so cool about that is that this will actually be the oldest lake environment ever explored by a rover on Mars. So this will be the oldest sort of aqueous environment yet encountered by any spacecraft on Mars. And then the ages get older and older as you go west. So there's 4 billion year old rocks to the west, those ones. And then what's really cool is outside the crater, the rocks are even older. We think they may go all the way back to the formation of Mars, perhaps all the way back to 4.4 billion years ago. So if and when we eventually drive out of the crater, and that's what we're hoping to do in about maybe 1.5 Mars years, we'll be able to explore the very deepest time in Martian history when the planet formed. So you see, by driving across this stratigraphy, as we call it, these rock layers, let's say we land with a place where there's a kind of target there and we move to the right. As we drive across this, we'll be driving across ancient Martian history, and we'll be sampling, we hope, and exploring each of these locations. We don't know exactly where we're going to land, so this is kind of a notional traverse that we might do. But you see, just in this maybe 10-kilometer traverse, we will explore, perhaps 2 billion years of Martian history. And there's very, very few places on Earth where such a short little drive you could explore so much. Okay, so let me just end by the second question that I mentioned. So why is Mars's crust so magnetic? So we saw earlier that there was evidence for an ancient magnetic field on Mars, and that today we have an echo or fossil of this magnetic field in the form of magnetic rocks on the surface. So they're magnetic because they formed in a magnetic field, but they also must have tons of magnetic materials in them. And in particular, a mineral that makes up lodestone on the Earth called magnetite, which is a sort of major, was an ancient mineral that was used for making lodestones in classical Greece. So here's a picture of a different landing site. This is Gale Crater, which was explored by the Curiosity rover. It's being explored right now, the last rover to land on Mars. And one of the most exciting discoveries of the Curiosity rover is that mudstones, like the one shown here on the right, which it drilled, it's not bringing samples back, but it measured them in situ, is full of magnetite, maybe 10 weight percent. And that's so much magnetite that it seems it's been hypothesized that this is evidence of large scale aqueous alteration and fluid flow in the Martian crust. And in fact, it's also been suggested that not only does this provide evidence of liquid water, but in fact that there was hydrogen being produced in the process of altering the rock to make this magnetite. And this hydrogen could be an energy source. So another question we hope to answer is, what is the origin of this very magnetic crust? And is it indeed a signature of an ancient habitable environment on Mars? So with that, I'm going to pass it to Tanya, who's going to talk all about the questions of life on Mars.
So as Ben mentioned, Jezero crater is the oldest sedimentary environment to be explored on Mars, but it's also by far the oldest sedimentary environment and by far the best preserved sedimentary environment on any planet, including Earth. And as such, it gives us really an unprecedented opportunity to ask what life was like at the time, whether life was evolving in different places of the solar system. So this is one of the questions that really motivates this mission and the exploration of Jezero crater. So let's see what is known about life and the evolution of life at the time that is sampled by these sediments in Jezero crater. So here's what we know, and this is mainly derived from the studies of any record on Earth. This is the inferred age of Jezero crater. So there is a range from about 3.5, 3.6 billion years ago, going all the way into perhaps 4 billion years ago. And here's what we think happened. So we first have to have a stable planet that doesn't receive too many meteorite impacts, so it can hold liquid water. And we know on Earth, stable hydrosphere, so some big bodies of water were present around 4.2 billion years ago. And here's the real black box of evolution. We really don't know how processes came to be to form a cell. So we think that happened through a number of reactions that form prebiotic chemistry, meaning we had reactions that were selecting for specific compounds that then came together to form cells. So lipids, some kind of nucleic acid, proteins, amino acids, and so on. And so all of that perhaps happened really fast. We don't really know. So all of these are just cartoons of what we think happened. Prebiotic chemistry to some kind of information molecule to the world where all these information molecules are competing and some are getting selected to then form first cells, something that will be enclosed. And we can recognize because of its interactions with sediments. And here is the first record of what we think is the cellular life. And that happens on Earth at 3.4 billion years ago. So we simply have no record of anything that came before. And Mars can allow us to sample that. And particularly what I'm excited about is that these incredibly old sediments allow us to even ask what this prebiotic route to life may have been. Maybe there were some reactions happening on the surface of Mars and Earth as well. So by sampling Mars, we can actually be able to say how life came to be on Earth as well. And a lot of these prebiotic precursors to cellular life are thought to have been formed on the surfaces of planets. So there are a lot of chemical experiments that people are doing in the lab and trying to produce. So here on the right, you see a bunch of molecules. And for those among us who are chemists, you can recognize some nucleotides, you can recognize some proteins, but everything you think should come in a cell. And all of that, amazingly, happens in a bunch of reactions that require very simple ingredients that happen on planetary surfaces. So we need access to light and UV radiation. We need hydrogen cyanide. We need SO2 or maybe hydrogen sulfide. We need minerals, ideally something rich in sulfur, all of which is entirely plausible on planetary surfaces, as well as we need processes that contain liquid water. So all of this happens in solutions, but processes that will concentrate certain reactants or flush away certain products. So we need freezing or we need evaporation. And what better environment for that to happen than a lake on Mars? So here is a potential sampling route at Jezero that can help us really probe rocks and sample rocks where we can hope to have some remnants of those kinds of chemistries or even emerging cellular life preserved. And one of the best potential types of rocks that we on Earth look for when looking for signs of life are rocks that contain a lot of clay minerals. And that is exactly what Ben was showing in his picture from Gale Crater. So sedimentary mudstones, and that is exactly the type of rock that we should expect somewhere around Delta. So as we land, we are likely to encounter some very fine-grained sedimentary rocks full of minerals that are known to trap organics. So that is great news for us. And something that we need to explore further, Mars is not Earth. So the sediments on Mars actually are chemically quite different and not representative of most sediments on Earth. So Ben showed this picture this is from Gale Crater. So we are yet to get pictures like this from Jezero Crater. But you see this darkish, very fine-grained material that is full of magnetite. And this material is thought to have been produced by the interactions of very fine-grained basalt with water and with perhaps some gases that were warming up the early Mars to keep the water liquid. And so what we're doing in the lab is putting those types of sediments, which are not too common on Earth in sedimentary environments, in water and putting some CO2 to see that, in fact, when you do that, their entire little nodules forming in the sediment under the water. And these tend to contain a lot of clay minerals similar to those found on Mars, and they happen to be magnetic. So we may be onto something here in identifying something that we can actually pick up on the surface of Mars and say, yes, this is actually likely to not even contain clays, not only clays, but also these clays may contain organics because the clays that form are well known, the types of clays to absorb organics. Another way to look for life would be in minerals that are known to well preserve the outlines of microbial cells well. So what you see on the left here are actually the oldest fossils of cyanobacteria, organisms that first figured out to make oxygen. And these are 2 billion years old. And so what you see here, all these individual vesicles are cells that formed a big cluster of cells. You can see some of that later. So what we are looking at are thin slices through silica-rich rocks that preserve cellular morphology amazingly well. And that silica is known to precipitate on the surfaces of even modern cyanobacteria cells. So really fossilization processes that happen, these bacteria can actually mediate their own preservation. So if you see silica, that is another good type of mineral that we should look for. And in fact, some orbital measurements indicate that silica is present on Mars. And Ben mentioned limestone around the outlines, the edges of the former lake. And it's not quite limestone. It is actually, limestone on Earth has calcium, and the minerals that are really abundant on Mars contain a lot more magnesium. And once again, Mars surprises us. It's not exactly the same as Earth, but there are some environments on Earth where these magnesium carbonate minerals form. These are some modern lakes. Here are pictures of a modern lake in Turkey that is in basaltic terrain. So a good analog for the lake Jezero Crater, the lake that was in Jezero Crater on Mars. And excitingly, all of these, you're seeing a lot of deposits, all of these minerals that form all of these light structures and some greenish on top. These minerals are magnesium carbonates, and a lot of them tend to preserve evidence of former microbial activity. So again, we are very excited to see, and we have no idea really what to expect the material on Mars to look like, but we will be ecstatic to see something like this and then look for signs of former microbial activity in those types of deposits. So what we are doing in preparation for landing on the side of sample return science that Ben and I are both members of, we are trying to understand all of these analogs on Earth that can help us guide the rover and tell it, you should really sample this rock and you should really check out that rock. we are learning how to detect minerals using all of these instruments that are on the rover and recognize features such as those nodules that I showed you. Perhaps those would be the best candidates for the preservation of organics. We are also working on developing the system to document and collect samples. These samples will be available to the entire humanity for decades to come to investigate if they're brought back on to Earth. And so we need to document them really well. We are also, for particularly Ben's purposes of anyone who is interested in this deep time evolution of magnetic field, figuring out ways how to orient samples, something that every geologist would do on Earth, but it's much harder to do with a rover on Mars. So to remember the position, relative position of the sample before it's scored relative to the rocks, because that contains a lot of positional information and information about the magnetic field. And so here is a potential exploration route. Don't take this as the final route at all. We still don't quite know where we'll land, but any plausible route that we can take offers the chance to sample multiple minerals and types of rocks that I mentioned. So if we land somewhere here and make our way towards the rim of the crater, we will be able to sample mudstones. We will be able to collect a lot of clay minerals. We may encounter some silica. We certainly will encounter carbonates. So these magnesium carbonates, and a lot of other rocks that are relevant to people who want to date the surfaces and want to investigate climate change and so on. And so to conclude, Perseverance will begin the Mars sample return campaign. So we will collect the samples, we will form cache, 1 or 2, and then the next subsequent legs of the Mars sample return campaign will go to Mars and work on retrieving the cache and bringing it to Earth. So the nominal plan for those samples is to be on Earth by 2031. The samples can tell us about a history of Martian climate and magnetism, as well as prebiotic and early biological evolution. And so really keep your fingers crossed for next Thursday. This is where you can watch it. And I will end by showing this flyover, the mesmerizing flyover of the route, potential Perseverance route at Jezero Crater.
Thank you very much.
Thank you very much.
Thank you so much, Tanya and Ben, for such an exciting presentation. And I just love this visualization so much. I think it's a perfect segue to show us the many potential different paths we could take throughout this Q&A as well. So I wanted to remind our alumni viewers before we begin our Q&A that they can post their questions in that Q&A feature on Zoom, and you can also upvote the questions you'd like to hear discussed. So now let's kick it off. We have a very highly upvoted question, and our alumni viewer asks, how do you know that that liquid flow lines that you mentioned earlier are made from water and not from any other liquid?
Want to take that one?
Yeah, well, that was debated for decades, because as I mentioned, and even going back to the 70s, we were aware of these so-called valley networks. And for a long time, it was kind of, there was a debate, there were some the most common volatile, so whole thing that makes liquid on the surfaces of planets is H2O. It's just a cosmically abundant molecule. So it's not going to be some very exotic type of thing, say made out of neodymium or something like that, right? Just because there's not a lot of it around. But the leading alternative was some kind of CO2 liquid, but it just doesn't have the right mechanical properties. And it turns out that the abundance is really low. And then most importantly, it was eventually found, large reservoirs of near subsurface ice were identified in the Martian crust from orbiters. So now we know there's an enormous amount of ice right beneath the surface, which would provide the reservoir for this. So it's a bunch of different pieces of evidence that make it the only plausible thing that could have carved that.
Also,
but it's a great question.
It's a great question, but you've probably seen every couple months, there is another paper reporting water on Mars. So we know there's a lot of water on Mars.
Yeah, Curiosity rover has actually now seen it, in the rocks in mineral form, H2O, and so we just know it's everywhere from the last, say, decade or so of data.
Got it. That's totally fantastic. And I wonder, Ben and Tanya, if we can stop sharing your slides so that we can see you both
Yeah,
on the
let's try to
big
do that.
screen.
Yeah.
I think people are
There we
really
go.
enjoying
All
the
right.
enthusiasm you're bringing to all of this. We have another question from an alumni viewer who notes that they're asking a rather impossible question here. So we have that caveat. They wonder, do you think Congress will fund a sample return mission? And if not, are there other options to return these samples?
The return, Mars sample return campaign is a coordinated effort between NASA and ESA. So
European Space Agency.
European Space Agency. So it's not just on the Congress, and there are strong systems in place. So I'm not too worried.
But it is
It
true,
is true.
that they haven't committed to doing this, and it's envisioned that there would be 2 downstream missions. So there'd be another lander that would have a little baby rover that'll drive out and go pick up the samples. They call it the fetch rover. And then it will go back to the lander, and the lander will actually blast off. So that's envisioned to be maybe the biggest payload delivered to another planet, because it needs to bring a rocket with it to blast back off, right? And then that'll put it in orbit around Mars, and another mission would then go pick up that thing in orbit around Mars and bring it back to Earth. So it's a very complicated, at least 3 mission sequence, including Mars 2020 Perseverance. And we'll see how that turns out. But our job, in order to make this a reality, is to select the most scientifically compelling samples that are so exciting and show so much promise for answering the questions that we talked about, that the world will just be compelled to bring them back. So that's the best way we can do, the thing we can do to make this a reality is just find some really cool samples, and that'll hopefully, drive the rest of this.
And there's a lot of technology demonstration as well. So if you watch the movie The Martian, it's really the same idea of picking things up from the surface of Mars and then bringing them to the orbit and then bringing something from there to Earth. So just demonstrating we can do that would be incredible and important.
I like that a lot. I remember in The Martian, it's like, bring Mark Watney home. We're bringing Mars home with us. So that's totally exciting and super fun. And we have a question that actually leads into this really well. Our viewer wonders, when you do get those samples back from Mars and they come to Earth, how will you protect us from potential contamination?
There is a planetary, so NASA has a lot of things, and they have a very stringent planetary protection program. So nothing can be sent to Mars without being thoroughly sterilized according to very, very stringent criteria. And this program will be involved in treating samples and really handling them in the safest possible way. So they're doing their job.
And there's a heritage for that. So when they brought this Apollo samples back, although we knew there weren't like big cities on the moon, they were still treated in the early days, as possible, containing possible life forms. And so NASA has incredible expertise at handling these samples in a clean way that both protects the Earth and the sample. Particularly in Johnson Space Center is one of the world leading centers for extraterrestrial sample curation, as they call it.
But those steps are still being worked out, because we still need to collect the samples first.
Right, that's a good point. And we're wondering, some of our viewers are wondering about some of the specific instruments that are going to be on board Perseverance, and they're wondering, is it possible to do isotopic analysis on the rover that you could use to maybe indicate biologic processes?
Not with this rover. We don't have a mass spectrometer on this rover. So there are a lot of constraints because of the caching and sampling equipment, and also having to carry all these samples, although they're pencil thin, but there are 40 of them, out of which 30 can be returned to Earth. So there's just not enough, there's too much weight and not enough space to put all of the instruments we could desire. So that's that partly, well, that is offset by really the return of samples to Earth, where we can use all of these mass spectrometers, but not on this particular mission, unlike the Curiosity rover or I think the Viking and.
Yeah, I mean, the thing that's so exciting, one of the many things that's so exciting about this is that, bring the samples back, generations of people will measure these all over the world. And it's, the type of measurements that will be made and the capability that future investigators will have is almost hard to conceive. So things will be done with these that none of us have ever dreamed of right now, and using instruments that can have sensitivity and spatial resolution that far outstrip what we even have in Earth laboratories today, much less what you could put on a rover. So that's the real, key advance of this mission, is the opportunity to basically study them for as long as we have them on the Earth. So.
That's totally exciting, and I'm really excited to see what comes from that. Now, we have a few questions. A few of our viewers have asked the same question, and they're wondering, you mentioned meteorites earlier in your presentation. How do we know that these meteorites are actually from Mars in the first place?
Should I take that one?
Of course you have to take that one.
I have a PhD on this, so I love this question because it is amazing. So basically, the first Martian meteorites were actually found in the 19th century, and they didn't realize that they were from Mars. It was only in around 1980 or so that we began to realize that these rocks that had been in our collections for decades were actually from Mars. And one of the most important things that led to that realization is, well, first of all, they started to find out that they were very young by the standards of meteorites. So most meteorites are really old because they formed on asteroids, which are really small bodies. So they just cooled off really quickly and had no geologic activity after maybe a few 100 million years. So here were rocks from some body that were only 180 million years old, and many of them. And they were basalts. So they came from a body that underwent melting and was hot that recently. But the thing that really nailed it was that it turned out that Viking lander, so that Viking mission that I showed you earlier with a picture from orbit of the craters that are being eroded, it also had landers associated with it. And the landers measured the composition of the present day Martian atmosphere. And it just so turned out that some of these meteorites have gas trapped inside them, whose composition, both elementally and isotopically, matches spectacularly with what the Viking landers measured and subsequent rows of men. So if you plot like abundance and these elements and these molecules and isotopes of Martian atmosphere versus what in this rock, you get this spectacular one-to-one line. And so that's what convinced people.
Got it. That's super cool. And a few folks are wondering, what other types of measurements can you get on the rover that you're most excited about, and why? What kind of analysis can we do?
We can do quite a few analysis with the rover. So one of the most important parts of any Mars mission are pictures. We all love pictures. We all mesmerized by the landscapes and panoramas, and also close-ups of crazy features that we may encounter. So I am personally very excited to see, for example, what do these carbonates look like? Because I don't have a good idea. So pictures will be major, but we do have some instruments. Ben mentioned some spectrometers that allow us to see mineral spectral signals. So we will be able to say, oh, this looks like a carbonate, but then let's shoot a laser beam and see whether it matches the spectral signature of a carbonate. So we will have a lot of confirmation that way. There are also instruments on the rover arm, so where the drill is as well. And that allows us to come really close to the surface. It's really like what is illustrated in the opening picture, the rendering. You can come really close to within a centimeter, 2 centimeters close to the rock and image the surface. So it's almost like a microscope. There is this imager, Watson, that shows if the grains are big enough, you see individual mineral grains. Also, there is an instrument called Sherlock, so we can map the mineral composition of even these individual grains. There is an instrument called Pixel that tells us what elements are present, also close up. So all of these data sets can go together and we can use them to confirm this is the rock we think it is, and this is why we should sample it.
That is so exciting. It's just amazing to think of the type of technology we're able to bring up there and use to get all this rich information. So we're gonna focus these tools on Jezero, but some of our attendees are wondering, how many sites did you actually consider before focusing on Jezero in the first place?
Great question. You want to take that one?
Oh man, so there was a process that went on for years, and it was a community driven process where I think several dozen sites they initially started out with as proposed landing sites. And then over a period of years, with multiple meetings, it was whittled down to this one. So, so yeah, I started out with at least dozens of serious proposals, and you know that you can't go anywhere because there's restrictions in the technological restrictions about where you can land. But one thing that's special about this mission is it has it's going to be landing in a very similar way to the Curiosity rover landing. Some of you may have heard of the 7 Minutes of Terror. If you haven't, I strongly recommend you search 7 Minutes of Terror and watch the video because it's awesome.
You will never think about the landing on Mars the same way again.
So, you know, the 7 Minutes of Terror involves, you know, ultimately being lowered on a basically a few different ropes to the surface. But one thing that's different about this rover as opposed to the previous one is it has something called Terrain Relative Navigation, TRN, which basically has a little map of the surface from orbital data inside of itself. And it takes pictures as it goes down and compares that to the internal map that it has and actually steers itself to land in a safe place. So because of this technological advance, we could go to places that we couldn't land before. And that's ultimately one of the things that enabled us to go to this landing site.
That's awesome.
And I have to say there, can I just add, it's something I shouldn't have been surprised, but it was really nice to learn that so many of the engineers who are involved in the design of all of these tools and methods and improvements are MIT graduates.
Yeah.
And now they work at JPL and are landing rovers on Mars.
It is totally awesome. And I don't think I'll forget how the excitement in the room at the last Mars 2020 landing site workshop, that's actually where I met Ben for the first time in California. But there was a lot of debate about where to land and what was a good place and all about the rover's path. And that brings me to a really fun question by one of our attendees. They said that they noticed that on each of your separate slides, the potential sampling routes differed. And if that was intentional, they wondered if, what's the cost of that? It was?
That is that's paying attention to the talk. That is partly intentional because we are still developing, we don't know exactly where we'll land. And we are prepared for various scenarios, none of which are directly reflected in our presentations because we cannot release the routes yet.
But they're notional anyway. So,
they're notional.
You know, what we did over the last few months in preparation for this is we gamed out different landing sites within the ellipse because we really don't know where it's going to. And it turns out, depending on where you land, you get quite a different mission. And so that still didn't by any means exhaust the number of possibilities, but it kind of trained us how to work together as a team and how to like figure this out and think about what are the general scientific and engineering trades we might want to make when we get there. So that's one of the main activities after we land. There's kind of a 90-day period where it's, you know, we're not going to be driving. We're basically going to be checking out doing various initial checkout and making sure everything works. We'll fly the helicopter during that period. But the major scientific activity, one of them will be, now we know where we landed, now let's plan out a route. So we'll go through that process all over again.
But we'll be much better prepared. So it won't take forever.
Supposedly.
Well,
And, you know, after that 90-day period you mentioned, Ben, I mean, people are wondering with with whatever path is actually ultimately chosen, how long is that going to actually take for the rover to traverse it all?
So the prime mission, the duration of the prime mission is about, it's 1.5 Mars years.
Approximately, we haven't quite.
Approximately. It's still
finalized.
being figured out where we need to end up by that time, whether we think we have to make it to the crater rim. Because if whoever was paying close attention to our hastily drawn potential routes saw that, and actually you can see it, well, we don't need to share the slides now, but we actually will not, ideally, if the rover lasts, which it should, we should exit the crater and go into the terrains that are much older than the crater itself, which are, again, the types of terrains we haven't encountered yet, and offer the opportunities to probe all these questions that we actually can probe in Jezero crater. So that is another perhaps year and a half of Martian year and a half, so more than 2 Earth years of exploration. And that'll be true exploration because these terrains are unlike anything else we've seen before.
Wow, that is super duper cool. We have a question that's a listener that's wondering, and maybe this would be a good question for Ben in particular. What happened to Mars's magnetic field? Can you tell us a little bit more about that story?
Yeah, so that's unknown. We know, as I said, that there was an ancient magnetic field because we have meteorites that are magnetized that have this fossil record of it, and we can see it coming out of the surface. We know it doesn't have one today. So we must have turned off at some point, and we see that in other bodies as well, like the moon, for example. So what makes a magnetic field in the first place? Well, we think the way it works is that there's a core made out of metallic liquid, which is conducting. So electrical currents can flow in it. And currents are generated by the mechanical churning of that fluid, okay? Once you move a conducting fluid in the presence of even a very weak magnetic field, it'll lead to currents. And those currents will then generate the large scale magnetic field that we call the dynamo. And so the fundamental requirement there is that one, you have a conducting fluid, which we're sure Mars has a core, we know that. But that core needs to be moving and churning. So probably somehow that core stopped vigorously churning, and that led to the death of this magnetic field. Now, why did that happen? Well, on the Earth, what makes it churn is the cooling of the core. Basically, heat comes out of the core, and just like your lava lamp, that leads to what we call convection, hot stuff rising. It rises to the top of the core where it's cold, then it cools off and it sinks. And then other hot stuff rises and it cools off and it sinks. And that large scale motion, which we call convection, we think is what's driving the Earth's dynamo. So probably somehow that stopped on Mars. Now, why did that stop? You can keep going deeper and deeper into this rabbit hole if you want. But one idea is that early Mars had plate tectonics the way the Earth did. So Earth, you may or not know, has these rigid plates that move all across the surface and then dive down one beneath the other, like what's happening underneath Japan, for example. It's where we get earthquakes. And then the other places, the rocks are formed like the mid-ocean ridges in the Atlantic. That's basically where the rocks are rising. So that's basically the surface manifestation of the cooling of the mantle, the rocky outer part of the Earth, which we call plate tectonics. So Mars may have done the same thing, but then that stopped at some point. And once that stopped, heat was no longer being extracted from the core below it, since the rocks above it were now no longer cooling off. And then that in turn led convection in the core to shut down. So maybe I gave you a longer answer than you wanted, but to boil it down, it's probably somehow related to basically the fact that the core stopped churning as heat was no longer extracted out of it.
And Mars is much smaller than Earth, so that is, the more mass you have, the longer you churn.
Thank you for pointing that out. Yeah,
Yes.
so Mars is
this is fun. This is like a geology lecture.
Yeah, so Mars is smaller, so its surface area to volume ratio is higher, and so it cooled off more quickly. That's probably broadly compared to the Earth. That's like the broad reason why this is happening.
Yeah, and speaking of all of this and the differences between, Earth and Mars, the instrumentation that we're sending up there, and the rover was all developed on Earth in place with this magnetic field, and we have this very active dynamo and everything. So does that affect how the instruments run on Mars? Someone is wondering.
How does what affect?
Oh,
Sorry.
that there's not as much like active magnetic activity there.
Well, it turns out, as you know, we use the Earth's magnetic field to navigate. Many instruments do that, even satellites. So that's one thing you can't do on Mars. You can't put a compass on the rover. And in fact, if you did, you get lost really quickly because there's a really strong magnetic field on the surface in many places, but it's just not pointing north. It's just coming out of the rocks. So that would maybe be the biggest difference, is there's no magnetic orientation on Mars.
Got it. And we have a question from a very excited listener, and they were wondering, why can't we get the samples back sooner than planned?
You want to take them?
Well, it takes a long time for the rover. It doesn't move all that fast. And also everything takes time, getting the sequences of instructions for the rover what to do and getting all these analyses done before we decide to sample something. So every sample will take probably 10 days, 12 days after we decide to sample. And there is a limited time. The rover has a lifetime that is qualified, and it doesn't, we can hope it lasts a long time, but there is an engineering constraint on that. So we first need to collect all of these samples. Then to maximize or to minimize the time, how to get to Mars and how to send a fetch rover and to minimize some energy requirements, there are windows of opportunity when we can send a fetch rover. So the fetch rover has to wait for our rover to do its job. And the fetch rover then has to go there at a particular time. And then the next, it is just so we can send one rover to do all of it because of the weight constraints. It'll be prohibitively expensive to send something with enough fuel to put the rover on the surface and then take a rover back and go against Mars's gravity and bring everything to Earth.
Yeah, it's the same reason why when they launch a rocket on the Earth, it has stages that drop away as the fuels are empty. You don't want to bring everything on mission, because then the amount of fuel that would be required to do that in the rockets, and it would just be prohibitive. So it has to be staged, just like a launch from the Earth.
Got it.
Just like the movie.
Exactly, yeah. So we have an attendee who's wondering about the expected accuracy of the landing position. I mean, how do we control all of that from here?
Well, we have a landing ellipse, which we showed you in that movie, and it's smaller than past missions because of the terrain relative navigation. And I also, it has a second innovation, hopefully I get this right, called the range trigger, which before, apparently when it deployed, I believe that the way you guys can check, all of you online, this is right or not.
Googling.
But when it triggers the parachute, it's going to do it based on its altitude rather than its velocity. And apparently that seemingly subtle change, which it'll be using like a radar, I think, to determine that subtle change of when it triggers that the parachute apparently makes a big difference in its accuracy as well. So there are a few things like that have enabled the landing site here.
Got it. And now we're wondering, you mentioned the European Space Agency briefly in one of your earlier answers. Can you tell us about what other countries are collaborating with us for this Mars mission?
So some of the instruments on the rover are made by French scientists. The MEDA instrument is, I think, Spanish. There are Norwegians who built the radar. What am I missing? There are French scientists, yes, SuperChem. There are parts of SuperChem, this laser shooting instrument that will ionize some of the rocks to see what elements are present. So that is done in France, partly partly in New Mexico.
And then the return sample scientists are from all over Europe
Yeah.
as well. So there's almost half the team are European return sample scientists. So they're from lots of different countries.
Wonderful. So it's really quite a global effort, and that's wonderful. We're using every resource we have on Earth to get to Mars and back. So that's absolutely exciting. Now we have time for just a couple more questions, and we've received so many, over 70 in the chat and growing. But some people are wondering about some basics about this mission. So I wonder if we can kind of do a rapid fire couple of questions to close. So first question is, what is the diameter of the Jezero crater?
50 kilometers.
We passed that test.
Done.
Congrats, that was really
Roughly.
good. And next
There's a
question. Next question. How big is the rover?
It's like a car sized.
It's a car.
Volkswagen Bug like. Not a big car, not a big SUV.
Fantastic. And when the samples are hopefully returned to Earth, where are they supposed to land? Where are we going to initially receive them?
I don't think that's been worked out yet. So yeah, often in sample return missions, they send them to deserts. So for example, in American West, or the Hayabusa 2 mission from asteroids just landed in the desert of Western Australia, and in Australia, somewhere in Australia. So probably someplace like that, but I don't think it's been worked out yet.
Got it. Well, I mean, these alums always forward thinking, they know what it takes. So that's absolutely wonderful. Well, I wanted to begin our closing now. Thank you so much to our wonderful experts for all their expertise. So on behalf of the Alumni Association, thanks to all our fantastic attendees for tuning into this MIT Faculty Forum online broadcast. And once again, thanks to our incredible experts. We'll be sure to forward all the questions asked in the Q&A to our speakers today, and alumni office staff will keep the chat window open for a few more minutes, approximately 15 for discussion purposes. So feel free to tell us where you're coming from and whether you enjoyed today's presentation. This broadcast, in case you weren't able to stick around for the whole thing, will be available on the MIT Alumni Association YouTube channel within a week or so. So with that, I wanted to thank you all for joining us today. Thanks for spending some time with us, and I'm super excited for the events next week. I'm sure you all are.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.